Now I'm going to talk about the vertex transformation, the sort of main topic for the day. Transformation. I'm going to sketch now partial pipeline. That's the part of the pipeline that does the vertex transformation. The entire graphics pipeline, as you remember, has more than just vertex processing and also has fragment processing and other stuff. But the vertex processing part, I'm going to sort of zoom in now and go a little more into detail with. I think I used this. Actually, it's maybe this small font for that because, yeah, it's a little small here, but it's a bigger resolution. So when you look at it later, it should be okay. It's readable. Barely. Modeling transform is the first thing we have. Then we have something called a viewing transform. And then we have projection transform. Those are the, that's the wrong one. Those are the model view projection transforms, and this is what we mainly do in vertex shaders, these three. Then we have something called a perspective division. And finally, viewport transform. And let me just put some little boxes. Black. There. Oops. Okay. Just draw a few arrows. It's just to illustrate that it's a pipeline, so vertices come in at one end and come out at the other. Transformed and ready for the screen. We usually have graphics applications. We have a bunch of, have some data, some mesh data or some generated geometry or something. Usually it's we look at a world with some objects in it. And for that reason, because the world is often composed of objects that can move in relation to each other, and we want to easily be able to move those without modifying the vertex data directly, we have this modeling transform step. So every object that we want to, like a physical object, we want to be able to rotate and place in the world, we use a modeling transform for that. So we use a matrix actually, but here we call it a transform, to decide where each object should be in the world and how it should be oriented, and also how it should be scaled actually. So make it bigger or smaller using this as well. So on the left here, in comes the raw vertex data from like a model we made in Max or Maya or something like that, or some procedural data maybe, or some little primitives we use in Unity like spheres and boxes and stuff like that. And that is defined in its own local space. So it has its own little coordinate system in it that doesn't, where the vertices are always stays the same in this local coordinate space. And then we sort of move this coordinate space around in the world using this transform. And you may remember from the vector repetition last time we have something called a vector base that we use, which is like 3 unit vectors that can contrive a coordinate system that is put somewhere in the world space and oriented in some way, and this is how we do it. So we transform the vertex data that are defined in this local space using a base like this, that we can move this base around and place it in the world. Yeah. So as we go through this, I will note the space that we are in the various stages here. Do something like this, and then. So when the vertex data comes in, we are in what we call object space or model space, and I think I wrote on the slide I wrote coordinates instead, but it's the same as the space. Object model coordinates. So this is to say where at this stage in which space are the vertices defined. At this stage the vertices are defined in local object model coordinates. And what the transform does is that it places all the vertices of this particular object in a common world space. So all the objects are now in the same space. And we call that world coordinates. Then we have the viewing transform, and that is the virtual camera that we use. So we can objects placed in world space, but really we want to also, usually in applications like this, we would like to move the camera as if it were an object. So we transform all the geometry from the world space into what we call a camera space or a view space. And that's basically a space that is defined by the camera's local coordinate system. So imagine a vector base where the x, y, and z axis are at the focal point of the camera, and we have like an up vector that decides what is to be up in the picture and so on. Get back to that a little bit later, but that's what we call the viewing transform, or sometimes also the camera transform. But in general, this word viewing, we use that to describe a transformation to a camera space. We of course call those, I can also, view I coordinates. I put that. We could say camera coordinates as well. It's the same thing. Then we do the projection transform. So imagine we have all the vertices are defined in a 3D space that has its origin at the camera's focal point. That's basically the purpose of those two steps. Now we want to look at it in. We want to project it because the screen is a two-dimensional thing. It can't show 3 dimensions, so we have to collapse this 3-dimensional space or image, or what you might call it, into something that's 2D for the screen. And but so 2 major ways of doing that. The most common in 3D graphics is what is called a perspective transform. That is what similar to what our eye does. So when we look at something, the further away it gets, the smaller it gets. We can't actually see that it's far away, but we can see that it gets smaller, and that's a perspective transform. But we also use an orthographic transform sometimes, and that's a transform where stuff doesn't get smaller when it's further away. So we can choose one or the other, and regardless, this transform, this turning 3D into 2D, that happens at this stage here, the projection transform. And we call this clip coordinates. For some reason it's not so logical, but that's the name we give it. And then this perspective division is a separate step because it's mathematically something else. It's actually not an affine transform. It's not something we can do with the matrix. So it's put in a separate stage for this reason. And of course it only happens if we use a perspective transform in the projection step. If we have orthographic projection, this perspective division gets switched off. It doesn't happen. And this is a very long word. Color. Yeah. Normalized device coordinates. It's called. get back to that later, so I won't talk so much about that. The final transform, viewport transform, is used for. I mean, a viewport is a definition of which pixels on the screen should the rendering take place in. So usually it's a rectangle of pixels, usually maybe the whole screen if it's a full screen application or some window. So here it would be like 1024 by 768 rectangle of pixels. It's also sort of equivalent to what we saw last time called the frame buffer. This is a pretty fixed transform that the hardware just does. It just maps the projected and the transformed and projected geometry into the screen pixels. I think we call that screen space if I remember correctly. Screen window coordinates. Yeah. Yes, I will just put a little bit of annotation. This is the input side, and this over here is the output side, of course. And also, this I already mentioned this. We just put it on the slide as well. This fact that these three stages, they usually happen in the vertex shader. So the vertex shader usually does this, and we call this MVP model view prediction transform. And these stages here, choose a blue color, they happen in the hardware. So that's, I mean, it all happens in the hardware, of course, but it's less configurable. That's why we say that it happens in hardware. We can configure some parameters, like we can switch the perspective division on and off, and we can decide the viewport, but there's just a few parameters we set, and the hardware just does that all the time. Whereas this MVP is really up to us if we want to do it, because the vertex shader is a little program, so we can write an MVP projection, MVP transformation if we want, but we can also do something completely different or change it in some way.
What was the other one?
The other one?
Yeah.
Which other one?
The blue one. In the vertex shader?
You mean something equivalent to this?
I'm with that.
Okay. Yeah, there's a little. There's not much space, but as I will put these on the Moodle, so you can look at them later also. Just to be clear on that. Yeah. So that was a bit long, but it's also going through all of vertex transformation, you could say. The next topic is something called affine transformation, and that's mathematically how we do vertex transformation. The word affine is something that is sort of in opposite or something else than what we also call a linear transformation. So this is not a linear transformation, it's an affine transformation, which is slightly different. I wanted to use here this dolphin I had from before. Let's find that. Where is that? Yeah. So we have, where did that go? Oops, it's not the one. Ah, where did my where did my palette go? Sorry about this. There, okay. It reappeared magically. Again, the input data is usually, like, we call this a mesh. Mesh is a mesh is really just a bunch of triangles. It's just a way of denoting the objects that we work with. And every object like this is defined in its own coordinate system. So, oh, actually, I'll put this the other way because we do that in Unity. Like this. So it has this coordinate system, and at the center here, like if there's a vertex at the center, it would have the coordinates 0, 0, 0. And the vertex coordinates are defined in this coordinate system. So if you look at a single vertex here, as you probably also remember from last time, we used a vector to denote it. And it has 3 coordinates, X, Y, Z. And vector notation here, so there. We can now, in order to do, for example, the model transform, model to world space transform, also true for the view space transform, is we can apply an affine transformation, which is multiplying by a matrix. So I put this down here, put some dots to denote some of the elements, because it doesn't really matter what they are at this point. They just have some values. And it's the top 3 rows of the affine matrix. The last row, as you remember, is always like this. And the multiplication we do is the matrix by a vector. And the vector that we use, I mean, we cannot multiply this vector by this matrix because they are not. There are only three rows in the vector, and there are 4 rows in the columns in the matrix. So we do like this. Put a 1 here. And this is also part of this. There's also another convention of these affine transformations, is that if we have a vector, a position, a vertex that denotes the position in space, then we add a 4th element, which is a 1. And there are there are mathematical reasons for this, and you can find those in the book, why this 1 is there. Very small rule to remember is that if there's a 1 here, then we're talking about a position in space, and if there's a 0 here, then we're talking about a vector, a direction. So it's actually a way to distinguish a position and a vector in affine transformations. And this is a matrix multiplication. And the result of that is, let's say we are working with the model transform here, then the object will be transformed from its own local space into world space. And the position of the object is decided by the values of this matrix. So we say this is the world coordinate system. And just to illustrate this, I will transform this object a little bit. Rotate it. This, and maybe make it a little smaller. 50%. And I will just redraw this local coordinate system that's in some way just still exists, although everything is now transformed into world space. Just put I did a little strange ordering in this slide, so it's a little more clear. 1, 2, 3. Yes. So we use what we call an affine transformation. Affine transformation being a multiplication, a matrix multiplication by an affine matrix to accomplish everything with vertex transformation, at least all the shader defined parts. In this case, the model transformation. And I will do another slide about this matrix that we use and introduce a few more terms on there. What do you call it? Affine transformation matrices. So again, these little dots are just elements of the matrix that have values that are a little more intricate to calculate. There. The bottom row that we always know is like this. And the 1. Now this actually has a relation to linear transformations. I talked a bit about linear transformations last time with vectors, with what we call linear combinations. And that is equivalent in the matrix, with matrices instead of vectors. So this part here, these 9 values here, you can look at those as a 3x3 matrix, like a submatrix. And that is what I choose to call the linear part of the transformations. And the linear part is rotation and scaling. Mainly. There's a third one that we can do, we don't use it so much, called shear, but rotation and scaling, the rotation and scaling of objects, rotating them and changing their size, is actually done by this part of the matrix. So manipulating those numbers means that we can control how objects are rotated and scaled in space. And if we see that as a 3x3 matrix, if we were to have like a system where we never wanted to do anything else than rotate or scale, then we didn't really need to use this 4x4 system. We could use 3x3 matrices instead and multiply by those, and that would be a linear transformation, not an affine transformation. So the affine, the reason we use affine transformations is of course these last dots that I haven't marked yet. I'm very good at this. Why not? These three values here, they are used for translation. Yeah. And I'll just make a quick note here of green. So I can call this fine part of the matrix. Put that in quotes. This is fixed 0, 0, 0, 1. So really what this affine transformation is, it's just a kind of a trick to use pure matrix multiplication to also do translation. To add, which basically adds a vector at the end. So we could also just multiply by 3 by 3 and then add a vector. That would be the same. That's actually what we're doing. But this is a trick to do this in just one operation. That's all it is. Do you feel a break coming up? Yeah. I think we'll there's one more slide, do it after the break, and then do another quiz. So let's do 10 minutes, is that okay?
Yeah.
So 20 minutes past 10.